Applications of quadratic functions. In this lesson, you will learn to find the domain and range of a quadratic function, determine the maximum and minimum values of a quadratic function, and then find the x and y intercepts of quadratic functions. Any number can be the input value of a quadratic function. So when we speak of the domain of quadratic function, thinking that the domain is the set of numbers that you could input to a function. Therefore, the domain of a quadratic function is just the set of all real numbers. Now, since parabolas have a maximum or a minimum point, the range is restricted. Now, since the vertex of the parabola will either be a maximum or a minimum, the range will consist of all y values greater than or equal to the y coordinate at the turning point of the parabola if the parabola opens up. Now, the range will consist of all y values less than or equal to the y value of the y coordinate if the parabola opens down. And so, as a general note on the domain and range of a quadratic function, always remember that the domain of any quadratic function is just the set of all real numbers, but the range is restricted. Now, how would we know what the restriction is? We're just going to look at the value for a, because the value for a tells us whether the graph is concave up or the graph opens upward or the graph opens downward. Now, if you are given the function for your quadratic formula in general form, which is this form here, ax squared plus bx plus c, to get the vertex of the parabola, you just need to get the x-coordinate of the vertex of the parabola first, and then plug it into the function, and then you get the y value for the vertex of your parabola. So if your a is positive, if a is greater than 0, you have a parabola that opens upward. And so therefore, your range are the set of y values greater than or equal to the y coordinate of your parabola. Or if you write it in interval notation, you could write it this way, where f of negative b over 2a is the y coordinate of your vertex. Now, similarly, when a is negative, then the range is the set of all y values less than or equal to the y coordinate of the vertex of your parabola. And you can write it this way if you're going to use an interval notation. Now, parabola may also be given in standard form. So if you're given in a parabola, the equation of your parabola in standard form, which is a times quantity x minus h squared plus k, to get the range of the quadratic function, you just need to get the value for k here, because this is the y coordinate of your vertex. And you use that same principle. If a is positive, you have a parabola that opens upward, so therefore the range are the y values greater than or equal to k. And if a is negative, you have a parabola that opens downward, so the y values or the range are the values of y less than or equal to k, where k is the y coordinate of your vertex. Now, to illustrate this, let us consider the following example. Find the domain and range of the given quadratic function. The quadratic function here is in its general form. So to get the domain and range, the domain is automatic. It is the set of all real numbers. But for the range, we need to get the y coordinate of your vertex. To do that, you have to compute first the x-coordinate of your vertex. And you can do so by getting the information for A, B, and C, and use the formula for the x-coordinate for the vertex as negative b over 2a. Now, b is the coefficient of your x, and a is the coefficient of your x squared. And so therefore b is equal to 1, and a is also equal to 1. So plugging in to our formula here, we have h, which is equal to negative 1/2. So take note, this h here is the x-coordinate of your vertex. So now you want to find the y-coordinate of your vertex. You can do so by plugging in the value for h to the given function. So we will evaluate the function at negative 1/2. So replacing all the x's here by negative 1/2, we have this expression here, and then you simplify that. Negative 1/2 squared is equal to 1/4, and this double negatives here will translate to a minus. Okay, so you just copy that. So therefore you have 1/4 minus 2 over 4 minus 24 over 4. That is actually rewriting this expression here. Then you get negative 25 over 4 as your y-coordinate. And now we can use this information to compute for the range of our quadratic function. So since this is the y-coordinate of our vertex, and our a here is equal to 1, which is greater than 0, therefore this parabola here has a graph that opens upward. So therefore the range is just the set of all y values that is greater than or equal to negative 25 over 4. So disregard this one, it's negative 25 over 4. Now let's consider another example. Find the domain and range of this quadratic function. The domain for any quadratic function is just the set of all real numbers. Now for the range, the values depends on whether the parabola, that is the graph of the quadratic function, opens upward or downward. And we would also be able to determine that by solving for the y-coordinate of the vertex of the parabola. So to do so, we will have to first get the information that we need to compute for the x-coordinate of the vertex of the parabola, so that in turn we can compute for the y-coordinate. So the x-coordinate for the vertex of the parabola can be computed using the formula here, negative b over 2a. And these values for a and b are actually the coefficients for the variables here. The coefficient for x squared is a, and the coefficient of x is your b, and the constant here is c if you need it. Now plugging into this formula here, negative b will be replaced by negative 2, and a will be replaced by negative 1. And then solving negative 2 divided by 2 times negative 1, and then taking into consideration the negative sign here, we have negative 1. Now because a is equal to negative 1 here, and so that means a is negative, the graph of the quadratic function is a parabola that opens downward. That means that we have a maximum value, that our vertex is the highest point in the graph. And the maximum value is the y-coordinate of the vertex. So to get the y-coordinate of the vertex, we just need to evaluate our function at the x-coordinate of the vertex. So evaluate it at h. We have h to be equal to negative 1. So we're just going to replace all the x's here by negative 1. With that, we have f of negative 1 equal to the negative of negative 1 squared minus 2 minus 1 plus 3. Simplifying this, we have 4. So therefore, since the parabola opens downward, the range are the y values. So the values of x, the maximum value is 4. And therefore, the range are all numbers less than 4. Less than or equal to 4. And so to help us visualize what we have just discussed, we can consider the graph here of the functions for each of the parabolas we have considered. So the first one is a parabola that opens upward. As you see here, this point here is the lowest point or the minimum point of the graph. And so the y value here is the minimum value. So therefore the range, if you look at the range is starting at this point because this is defined, the function is defined at that point. So starting at 1 up to positive infinity. Now if you have a graph that opens downward, the vertex is the highest point, the y value is the maximum value. So for your y values, you just have to, the 4 here, or the y coordinate of the vertex would be the maximum value. The range therefore will be from negative infinity up to this point here, which is y equal to 4. Now there are many real-world scenarios involving finding maximum or minimum value of a quadratic function. These applications involves area and revenue or some other quadratic functions. Now, so we want to illustrate here how you could use the method that we have discussed to solve for problems that involves quadratic functions. So for instance, given an application involving area or revenue, we want to use quadratic function to find the maximum, or you could also use the same technique to find the minimum. So first, you are to write the quadratic equation for the function. It's for the area or revenue function. And then you make sure that you write that in terms of one variable only. And then you find the vertex of the quadratic function and then determine the y value of the vertex. The y value is the maximum or the minimum depending on what the function is. For instance, let us consider this problem here. A gardener wants to enclose a rectangular space for a new vegetable garden. He purchased 100 feet of wire fencing to enclose 3 sides, and he will use a section of a backyard fence as the 4th side. Find a formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have a length of L. So first, let us look at the illustration for this problem here. So we have that this is the garden, and he would want to, so if this is the garden, he would want to use this. This is already existing, and so he want to enclose that garden by adding 3 more sides. So this one is already existing. Now, he purchased 100 feet of wire to enclose these 3 sides here. So that means that the total length for all these 3 sides here is equal to 100 feet. Now we want to find the formula for the area enclosed by the fence. So that means we want to find the area of this rectangular box here. We will just use the formula for the area of a rectangle. So if this is L, so if this is given to be L, then we will call this side here to be W. So if we have a rectangle, if this is L, this would also be L. And also we know that this 100 feet of wire fencing here is used to enclose all these 3 sides here. That means if I'm going to add L and then this W here and then another L here, that is equal to 100. So we will use that information to calculate for the formula, or to derive the formula for the area enclosed by the fence. Now we know that we only have 100 feet of fence available, and L plus W plus L is equal to 100. When you simplify that, that is 2L plus W equal to 100. And we can now solve for W in terms of L here by transposing this 2L on the other side of the equation. That's how we get W equal to 100 minus 2L. And then we use the formula for the rectangle, which is A equal to length times width, or the area for the rectangle is length times width. Now our length is just L, and we're able to express our width in terms of L. So we have L times 100 minus 2L, and simplifying that, we have 100L minus 2L squared. Now, this formula here represents the area of the fence in terms of the variable L. So this expression here is your area in terms of one variable L. Now, in the same problem here, suppose we want to find the dimensions should he make his vegetable garden to maximize the enclosed area. So in the previous slide, we are able to obtain the area of our parabola, which is A equal to negative 2L squared plus 100L. Notice that this is a parabola whose A is equal to negative 2. That means we have here a parabola that opens downward. That means that the vertex is at the maximum point of the function. So to get the dimensions that would maximize the enclosed area, we're just going to solve for the x-coordinate, or the x-coordinate of the vertex. We're going to solve for h. So with that, h in this case is just L, the variable is L, and the formula is just negative b over 2a. And then you just plug in the values. B is 100, so you have negative 100 divided by negative 2 times 2. So a is negative 2 times a, which is 2. So you have negative 100 divided by negative 4 is equal to 25. That means that L here is equal to 25. So if L is equal to 25, we can then proceed to compute for the width, and the width can be computed using the equation that we have, which is 2L plus W is equal to 100. Now, W in this case is just equal to 100 minus 2L. Now, if L is 25, 2 times 25 is 50. So that means that 100 minus 50 is equal to 50. So the W is 50 in this case. So the dimensions that would maximize the enclosed area is 25 by 50. So for the next application, we want to find the x and y intercepts of the quadratic function. As you recall, the y-intercept is the intersection at the y-axis, so you can solve that by setting x equal to 0. And the x-intercept is the intersection at the x-axis, and you can solve that by setting y equal to 0. So to solve for the y-intercept, we are just going to set x equal to 0. So you replace x equals 0. And in the function here, you just replace all the x's here by 0. So you have 0 minus 0 plus 3. So therefore the y-intercept is 3. So the y-intercept is the ordered pair 0, 3. For the x-intercept, you can compute for that by solving or by replacing your y to be y for 0. So if you set y or your f of x equal to 0, then you solve for this expression here, negative x squared minus 2x plus 3. You can solve that by factoring. So first you can factor out the negative sign, and then you will be left with x squared plus 2x plus 3. And then you can factor that easily into x plus 3 times x minus 1. And then equate it to 0. Now we have a rule, like a factor rule, that if we have two products that are equal to 0, that means that one of the factors there is equal to 0. So that way we can set one of the factors to 0, either one of them. So we have x plus 3 equal to 0, or we have x minus 1 equal to 0, and then you solve for x. So if x plus 3 is 0, we have x equals negative 3, and if x minus 1 is 0, you have x equals 1. These two values here are the x-intercepts. So the ordered pair that would correspond to x equal to negative 3 is the ordered pair negative 3, 0, and the ordered pair that would correspond to x equals 1 is 1, 0. So if you look at the graph, these 2 points here, that point and this point are the x-intercept, and this point here is the y-intercept. Now another example, find the y and the x-intercept of the quadratic function. So to do that, to compute for the y-intercept, all you need to do is just set here x equal to 0. So replace all the x's there by 0. That means you evaluate f at 0. So if you replace x by 0, you have 0 squared plus 0 minus 6, and that gives us negative 6. So negative 6 is the y-intercept. And the ordered pair that corresponds to that is the ordered pair 0, negative 3. 0, negative 6. That is your y-intercept. For the x-intercept, we are going to set f of x equal to 0. And by setting f of x equal to 0, we have this equation here. And to solve for that equation, we're just going to factor out the quadratic function. So factoring out x squared minus x minus 6, we have x plus 3 times x minus 2 equal to 0. Now this product here is equal to 0. That means that one of the factors, x plus 3, might be equal to 0, or x minus 2 is equal to 0. Now if x plus 3 is equal to 0, then x is equal to negative 3. And if x minus 2 is equal to 0, then x is equal to 2. So these are the intercepts. X equals negative 3 and x is equal to 2. And that is the ordered pair for the x-intercept. That is the ordered pair negative 3, 0 and 2, 0. And so to summarize, if we are given a quadratic function in terms of f of x, and we want to find the y and the x-intercept, to find the y-intercept, you just evaluate f at 0. And to find the x-intercept, you are to solve the quadratic equation f of x equal to 0. That is, set y to 0 when you are to find the x-intercepts, and you set x to 0 if you are to find the y-intercept.